aslında kimse yok ya, ben şeyi sorayım. Bu hiperbol denklemini nasıl bulduk? Hangisi hiperbol denklemi? Benim kafama geldi.
Okay, so we are kind of going ahead of our schedule now, as one of your friends has pointed out. There is not much left to do, but we kind of still have 4 weeks. So I would rather spend more time on your questions in the following weeks. Yes?
Bu hiperbol denklemini nasıl bulduk?
Well, let's go over the dynamics. So what we were saying was, in relativistic mechanics, the Newton's second law is still correct if we take this form. It's not mass times the acceleration, but the force is the rate of change of linear momentum. And this linear momentum now is the linear momentum in relativistic kinematics, where m is just mass times u being the velocity of velocity of the object divided by 1 minus u squared over c squared. Now, if the force is constant, well, this is kind of trivial to evaluate. I will just put in some boundary conditions. I will set that p at t equal to 0 is 0. I will assume that we are in a reference frame in which the particle is initially at rest. So then p of t for a constant force is just F times t. And by using the definition of P, mu over square root of 1 minus u squared over c squared is F times t. So this already tells me that the velocity of the object at all times is in the direction of the force. Well, this is kind of natural. So you have an object at rest, you exert a force on it. Even in Newton's dynamics, you would expect the acceleration to be in the direction of the velocity of the object. Now, the acceleration to be in the direction of the force, the acceleration will always be in the direction of the force, and hence the velocity at every time will be just in the direction of the force. Well, of course, this doesn't hold if initially the momentum was non-zero. So we already know the direction. We can just pick the direction of the force to be our x direction. But then the velocity at all times will also be in the x direction at all times. So this equation basically tells me that mass times u, or u divided by square root of 1 minus u squared over c squared is just f over m times t. Well, this is just an equation for u. Let's solve that equation. U squared would be ft over m squared times 1 minus u squared over c squared. If I just move the u squares to the same side, u squared is equal to u squared times 1 plus ft over mc, all of it squared, is just ft over m squared, or u is just ft over m divided by square root of 1 plus ft over mc squared. Well, u is just the ordinary velocity. It's just dx by dt. And the right-hand side, we said that, okay, the right-hand side we can write it as, let's take the square root. And if you take its time derivative, well, the time derivative of this square root will be, first 1 over the square root. I already have it over here. I will have a factor 1/2, but then I need to take the derivative of this thing with respect to t. That will bring another factor of 2. So there's no factors 2 left. But here I have f over, from the derivative, I would get f over mc everything squared. Whereas here I only have a single factor of f over m. I have to cancel somehow the additional terms, additional factors, that I can do if I multiply by c squared m over f. So dx by dt is equal to d by dt of mc squared over f times 1 plus ft over mc, all of it squared. Now I will just choose my coordinate axis such that at t equal to 0, let's say x is also 0. So this just tells me that x of t is just mc squared over f square root of 1 minus ft over mc squared minus 1. This minus 1, I need that minus 1. Well, this is just a constant. When you take the derivative, that minus 1 doesn't change really anything. So I can just, when I'm integrating a differential equation, I can always add these constants. And that constant I have chosen such that my solution satisfies this boundary condition.
Şu boundary condition biz belirliyoruz değil mi hocam?
Yes, I'm just choosing my origin. So this is the trajectory of my particle. And we said that if t is very large, for very large values of t, you see in ordinary mechanics, if the force is constant, the acceleration is constant. Since the acceleration is constant, the velocity always increases linearly with time, and eventually it becomes faster than the speed of light. Here we see that the acceleration you see the velocity, or better, this is the velocity. Velocity doesn't increase with time linearly. You see there is this additional factor. And if you just compare it with Newtonian mechanics, F over m would be just the acceleration. If you multiply it by t, this is just acceleration times t. And acceleration times t is nothing but the speed that the object would have in Newtonian mechanics. So for times such that that speed is less than the speed of light, there is no difference between Newtonian mechanics and relativistic mechanics. But when the speed gets larger and larger, that is as time increases such that this factor becomes larger and larger, eventually the velocity just approaches c. Is how to see that for t very large, you can just ignore this factor 1. And here we have, when you take the square root, it just becomes ft over m times c. ft over m in the numerator and ft over m in the denominator, they cancel, and we end up having u is equal to c as t goes to infinity. Or here, x of t as t goes to infinity, x of t just becomes well, let's just work it out. Again, I just ignore that factor 1 compared to this one. This will be huge. So if I ignore the 1, it's just ft over mc. Again, I can just ignore the 1. F's will cancel, M's will cancel, C will cancel. It's just C times T. Yeah, that's what we expect also, since the velocity, although there is a constant force acting on it as the object is approaching the speed of light, it just moves with constant velocity. You see, we have already made some choices. You see, this is one choice I made. I pick you can say that either you pick a reference frame, and you choose t equal to 0 to be the time at which the linear momentum is 0. That might be one case. Or you pick some time, you go to the reference frame in which the particle is at rest at that time. And then after that, once you choose your reference frame, you are dealing with that reference frame only. You are not changing reference frames.
Şimdi hocam bu bulduğumuz x'te Hiperbol denklemi yani.
Yes, it is the hyperbole. You see, to see whether it is a hyperbole or not, you should better write it in a slightly different form. If I convert it to xt plus mc squared over f, all of this squared, this should be equal to 1 plus ft over mc squared, or xt plus mc squared over f squared minus ft over mc squared equal to 1. This is the more conventional form of the hyperbole equation. What determines that it's a hyperbole is that the square of one coordinate and the square of the other coordinate have different signs. The trajectory is a function of time. If you also take into account the negative t, it just has this shape. Well, let me shift it slightly. This is the hyperbola we have. These are the trajectories for, this is the light cone at this point. And the reason why I shifted it is that in my boundary condition, I assume that at t equal to 0, my particle is at x is equal to 0. So the light cone that it intersects just starts at negative x.
Bu parçacık kendi light cone'un orijininde değil, ilerisinde mi hareket ediyor?
You see, everybody has their own light cone. There are infinitely many light cones. At every point there is a light cone. When this particle is at this point, its light cone is, well, kind of like that. Okay, the graph is not such a great graph, but it has its own light cone. When it is at this point, it has its own light cone. What this says is basically the particle will always remain inside the light cone of an observer at this point. But asymptotically, it will just approach its light cone. Yeah. Why should it be at the origin? the current time of what? You see, the reason why it is not at the origin is this -1 over here. Yeah, for very large times, this is negligible compared to this one. But if you just match it with if you just extend it by a line, that line crosses the t equal to 0 axis, that is my x-axis, at the point mc squared over minus mc squared over f. It basically tells me that if you send some light, the light and the particle, asymptotically they start moving together, but the light started faster. So it should start from behind. The light cannot start at the position of my particle and still asymptotically stay together.
Hocam bir de bu x'nin hani parabolü nasıl dönüştüğünü göreceğiz, nasıl yapacağız?
Well, the parabola is when the speed is slow. That's in Newtonian mechanics. If you look at the limit as t goes to 0 of x of t, how does it behave for small t? Well, if t is sufficiently small, meaning that this factor over here is much, much less than 1, I can use the Taylor expansion. This is equal to mc squared over f, 1 plus 1/2 ft over mc squared minus 1. They cancel. So this is f over m, 1 over 2, f over m t squared. Yes, as long as its speed is slow, this is nothing but the Newtonian acceleration. This is just 1 over 2a t squared. I don't have the v0t or plus the x0 terms because I started by assuming that initially my particle was at rest and it was at origin. Or to put it in other words, I chose a reference frame in which the particle was initially at rest at t equal to 0 and it was at the origin of my chosen reference frame. Let us do one more example. Not necessarily related with dynamics, but with length contraction. Let's just look at this system. We have a reference frame. Let's call it S, in which there is an object moving with length, moving with velocity u, and it has a length in this reference frame L. And then there's an alternative reference frame, S prime, which is moving with velocity v relative to the S reference frame. What is the length of this object? In the S prime reference frame. Now let's work it out together. You see, the catch here is kind of if you look at the first thing that comes to my mind, well, we have the length contraction, so the length in this S prime reference frame should be just L times square root of 1 minus V squared over C squared. Why not? So that would be the first guess. But the catch is kind of, when we drive the Lorentz contraction, we drive the length contraction relative to the reference frame in which the object was at rest. We first looked at the length of the object in a reference frame in which it was at rest. And then we compared that length to the length of the object in the reference frame that is moving. But here in the S reference frame, the object is not at rest. So the question is, does it hold? Does it really hold? We don't really know. We have to check. But one thing we can do is, well, first find the reference frame in which the object is at rest. What is the length of the object in that reference frame? Well, let's call L0 to be the length of the object in the reference frame in which it is at rest. Well, that reference frame is moving with a velocity u relative to the reference frame S. So this L0 is contracted. There is Lorentz contraction of this length L0, and it is contracted to 1 minus u squared over c squared. And this is the length that is measured in the S reference frame. Okay, conventions. L0, length in the reference frame in which the object is at rest. L, length in the reference frame, let me just use this RF reference frame, in the reference frame S. And L prime will be the length in the reference frame S prime. Well, in terms of L0, we can just straight away write what L prime should be. This is 1 minus u prime squared over c squared L0. U prime being the speed of the object relative to the reference frame in which the particle is at rest. Or L prime will be square root of 1 minus u prime squared over c squared. L0 is just L over square root of 1 minus u squared over c squared. So this is the length of the object observed in the S prime reference frame. Now there's still one thing we should calculate. What is u prime? How?
U eksi V bölü 1 kök içinde 1 eksi.
So, okay, u prime is u minus
V bölü 1. Ya da U artı V de olabilir aynı yönde oldukları için.
Now let's see. You see, u prime is the velocity of the S prime frame relative to the rest frame of the stick. Okay, now we are talking about 3 reference frames. V is the velocity of the S prime reference frame relative to the S reference frame. And now I introduced the 3rd reference frame, we can call it the S0 reference frame if you like. S0 reference frame is the reference frame in which L is at rest. So basically S0 reference frame is moving with velocity u. This is my S0 reference frame. Now then the question is, what is the velocity of the S prime reference frame relative to the S0 reference frame? Now, of course, the problem is, what about the signs? It's plus, minus, which one is plus, which one is minus? I mean, if you are not sure about the signs, you can just take some limiting cases. For example, you might imagine the case that u is 0. If u is 0, then S0 frame and S frame are basically the same frame. So the velocity of the S prime frame relative to the S0 should be just v, if u is 0. Well, that tells me that the sign of v should be basically plus. This is the limit when u is 0. This is consistent with that limit. But then there is the other limit that what if v is 0? Well, if v is 0, then the speed of the S prime reference frame relative to S0 frame should be minus u. So this is my u is minus, v is plus, the numerator doesn't change. So this is our u prime. So L prime is 1 minus 1 over c squared. U prime is v minus u divided by 1 minus c squared over, 1 minus u times v over c squared. All of the things squared, 1/2, divided by square root of 1 minus u squared over c squared L. Well, it doesn't look that nice. Let's try to simplify it a bit, so it might look a bit nicer. So L prime is equal to 1 over c times 1 minus uv over c squared. Well, what I'm doing is I'm basically taking that 1 over the square roots out of the square root sign. C squared 1 minus uv over c squared, or let me even, minus v times u v minus u squared to the power 1/2 divided by 1 minus u squared over c squared L. Well, let me open that parentheses and see if there are any simplifications over there. This will be 1 over c, 1 minus uv over c squared. I have c squared minus twice uv and plus u squared v squared over c squared minus v squared minus 2uv plus u squared to the power 1/2 divided by square root of 1 minus u squared over c squared. One over c, 1 minus uv over c squared. Well, here I have minus 2uv, here I have plus 2uv, I can just cancel them. C squared plus u squared v squared over c squared minus v squared minus u squared to the power 1/2 divided by 1 minus u squared over c squared. Times v squared over c squared minus u squared minus v squared. We can factorize that still. Oh, there's over c squared over c squared. This is equal to 1 over 1 minus uv over c squared. 1 minus u squared over c squared times 1 minus v squared over c squared divided by square root of 1 minus u squared over c squared. Or let's see, this 1 minus u squared over c squared under the square roots, they just cancel. And we have this final expression, L prime is equal to 1 minus v squared over c squared to the power 1/2 divided by 1 minus uv over c squared times L. So this factor is the only factor that we would naively have expected from length contraction, but there's this additional correction term. And in fact, if we just take the limit that u is 0, that is S is the reference frame in which our object is at rest, then in the S prime the length will be contracted by this much. Or the other limit will be if u and v, they are both equal to each other. In that case, S prime is the reference frame in which the object is at rest. The length in the L prime reference frame will be just equal to, now hold on. If u is equal to v, okay. If u is equal to v, then these factors are same except on the square root, so we would get L prime is equal to L over 1 minus v squared over c squared. That is what we already have. Use L0 should be if u is equal to v, if L0 should be L over 1 minus u squared over c squared. So at least our final expression is correct. in these limiting cases. So it's likely to be correct. It's likely that we didn't miss some factors, 1 or 2, or missed some signs somewhere.
Hocam şimdi V sıfır olunca o zaman o parçacığın uzunluğu değişmiyor. S prime.
V is equal to 0. Well, if V is equal to 0, it just means that S prime is equal to S. They are the same reference frame. So L prime is equal to L. Check. Second limiting case, V is equal to U. So in this reference frame, S prime is just S0. So L prime is equal to L, L0. If you look at our expression, L prime becomes 1 over square root of 1 minus V squared over C squared times L, which is L0. Check. Third case, V is equal to, U is equal to 0. Well, in this case, S is equal to S0. But this tells me that L prime is the contracted length, should be equal to 1 minus V squared over C squared L. Well, if you look at the above expression, just set U is equal to 0. This is indeed the case. So in these three limiting cases, our final expression makes sense. Well, these three limiting cases does not prove that our expression is correct, but nevertheless it strengthens our idea that we didn't make any mistake in the calculation, our claim.
Hocam peki direkt velocity addition yapıp ondan sonra length contraction'a geçebiliyor muyuz?
How?
S0'yu şey yapalım.
Well, you see, the problem is our length contraction formula is relevant only if L is L0. That's the only case we derived it for. Well, you see, that question doesn't make sense in the relativistic framework because there is no reference frame which moves at the speed of light c. It's just against the definition of reference frame. You can of course say that what if one of them is very close to the speed of light c? Just put in over there some speed very close to the speed of light c, and that's what you would get. It cannot be exactly equal to c.
Hocam şimdi biz hani rigid body için action reaction force and speed'in dengelemesini söylüyoruz. Hani dengelemezlerse parçalanır ya.
So?
Şimdi bu relativitede de action reaction.
Well, you see, let's say, what is the definition of a rigid body?
İki nokta arasındaki uzaklık değişmiyor.
Well, there's length contraction. The lengths change as the object accelerates. So the concept of rigid body itself is kind of problematic in relativistic dynamics. You first have to define what you really mean by a rigid body. No. E is not equal to mc squared. E is equal to square root of m squared c to the 4 plus p squared c squared. And m here is a constant. So, I mean, what are the properties of this effective mass? Then I will ask that question. That effective mass or that effective mass is not equal to the Newton's mass. No. What do you mean by length, to start with? That is basically changing. You see, for example, let's say we are accelerating nuclei in the LHC. The nuclei, most of the time, we just imagine some round object. Or just take the proton, we just imagine them as round objects. As they are accelerating, it's no longer round. It's an ellipse. It acquires a compressed sphere, more like a disk. It's not that it is being compressed by some additional force somewhere. It's just the definition of the length itself doesn't make any sense. I mean, it does make sense. The length is different what you mean by length is different in different reference frames. So that's why you have this change. You see, the concept of the length of an object is closely related to the concept of simultaneity. Because if you want to find the length of an object, you have to find the position of the boundary of the object at a given time. So simultaneously. But simultaneity in different reference frames means different things. Well, let's see. No, forget about the speed of light. Moving at the speed of light. Let's see. L is your length in the S reference frame. If you go, it is shorter than L0. Let's say you start moving. You start accelerating until you move at the speed u with the same speed, same velocity as the object. What you will observe is that the object gets longer and longer and longer until you reach u. If you keep accelerating, the object will start to get again shorter, shorter, and shorter. Or let's forget about u being accelerating or deaccelerating. Let's just assume the stick is accelerating and deaccelerating. You have your stick. Let's say you exert a force on it so that it starts accelerating. As it's accelerating, it gets shorter and shorter and shorter. Then you change the direction of the force and you cause it to decelerate. As it's decelerating, it will get longer and longer and longer. The spacing between the atoms will get shorter or longer. The atoms themselves will get compressed or spherical or disk-like. The nuclei themselves, they would be in their rest frame. If they are spherical in the frame in which they are moving, they will be just compressed. Not compressed by a force, but shortened in the direction of motion.
Ama bu kendisine göre değil mi? Bize göre.
Of course, relative to you. I mean, you see, let's say if you are moving at some, with the, let's say you have a meter stick, okay? And you are measuring the length of an object. As you are moving, let's say I'm measuring the length of this object as I have a meter stick. I'm just comparing the two. As we are moving together, I measure a distance. Let's say I measure the length of this object as twice my meter stick. You will also agree that it is twice my meter stick, by the way. But my meter stick, because my meter stick is shorter, this is shorter, still the ratio will be the same. So there's no way I can measure that distance, that contraction, if I'm moving with this. Because in my reference frame, the contraction does not exist. It started with being twice my meter stick. It will always stay twice my meter stick. Now, in fact, for every observer, this object, as we are moving together, will always be twice my meter stick. But if you want to measure the length of this object, you should use your meter stick, not mine. And my meter stick and your meter stick, they don't have the same length, neither in my reference frame nor in your reference frame.
Burada enerji neden kök içinde yazdık toplam enerji?
Where? Here. Well, that's the expression we have.
Buradan şey demiştik normalde, kinetik enerji eşittir E eksi E0 işte. Total enerji eksi rest enerji.
Okay, so. And that energy is this one. Well, you see, the reason why I wrote it explicitly with the square root is if I wrote that E squared is equal to this one, then you would say, what if energy is negative? So I just wanted to avoid that question. You will answer that question if you do some mathematical physics or particle physics. That negative energy problem arises in other places also, but for this lecture, I want to avoid it. So energy is equal to this expression. And the velocity of the object, by the way, the velocity of an object is always defined as Pc over E. This is the velocity of the object. Well, how do we know? Well, P, we had seen that it is mv over square root of 1 minus v squared over c squared. E is mc squared over square root of 1 minus v squared over c squared. So if you look at P over E, this is v over c squared, right? So the velocity of an object you can always write as p c squared over E or as pc over E times c. So the velocity of an object is p times c divided by square root of m squared c to the 4 plus pc squared times c or in terms of the magnitude, the speed is equal to the momentum divided by square root of m squared c squared plus the momentum squared times c. So you can look at certain cases. Mass can be zero. There is nothing that forbids the mass to be zero. In Newtonian dynamics, mass cannot be zero. But in special dynamics, special relativistic dynamics, there is nothing that would prevent a zero mass. For a zero mass object, the velocity the speed of the object is always c. So you see, c is not really the speed of light. C is the fundamental speed of nature. And any massless object should move at that speed. And photon turns out to be some massless object, and hence it moves at the speed c. So there is nothing special about light, with this c. It's just a fundamental speed limit of nature. Because light turns out to be a massless particle, it has to move at the speed c. Any other particle which is massless should also move at the speed c. Another limit is if m is not equal to 0, you see, m squared is, so this quantity is always larger than p squared, and hence its square root is always larger than p. P divided by some number that is larger than p is always less than 1, and hence the speed is always less than c. So in this sense, it doesn't make sense to ask about massive particles that are moving at the speed of light. Or it also doesn't make sense to say that what happens if a particle moves faster than the speed of light. Well, the only way is if m squared is negative. How can it be less than 0? Before we had the answer, well, that cannot be, so it's not possible. Now our answer is it can and cannot be. None of the particles that we will observe will have mass squared less than 0.
The enerjisinden mi bağlı olacak?
Well, what depends on the energy over here? I didn't make any assumption on the energy.
Yani enerjisi pozitifse kütlesi pozitif
No,
ama
no,
negatif.
no. Let's see. No. Let's give a 10-minute break, and then we will continue.